So we'll present some enhancements of MEMS microspeaker that we did. A lot of people work on this thing. They are all here, and they are from two universities. Yes. So the MEMS microspeaker that we developed is targeted for handheld applications such as tablets and mobile phones. So the problem with there's an echo. The problem when you integrate a speaker in a small device is that you take some alternatives, some micro-machined alternatives exist. I will focus only on the electrodynamics microspeakers that are the most used. So usually what is done is to take a macroscopic loudspeaker and to flatten it to obtain something like that. So what is obtained is obviously a flat structure with some magnets, a coil, and a membrane, a deformable membrane. So the consequences of that is you pass from 3D structures to 2D structures. You have the suspensions here and on the top that are simplified, so you don't guide anymore the surface, and the conic emissive surface that was quite rigid is now flat and deformable. So you obtain, you hinder a lot the performance of the microspeaker. So some developments have been made to obtain micro-machined speakers. So you need to have, for electrodynamic microspeaker, you need a strong magnetic field, a coil that will cause few losses, so low resistance, and light because it must be moving. You must have suspensions that, if possible, that must have low stiffness, they must be linear to allow big displacements, and yes, and high displacements. And the emissive surface, in the literature, they mainly are deformable, and our solution is to fabricate a very rigid emissive surface with very soft suspensions. So here is the device we developed. We bought some magnets to have a strong magnetic field. We electroplated a coil on a silicon surface, and micro-machining the silicon, we obtained some suspension arms, very soft, that allow a huge displacement out of plane. And we obtained, on the next slide, the microspeaker with the backside etching, deep reactive ion etching suspension ribs to obtain a very flat surface and very rigid surface. So with that, we have a micro-machined microspeaker that that allows to have some of the properties that are good for a good microspeaker. After that, as you notice, there are some holes here. So this is very bad for sound emission. So joint was developed by polymer forming, or either latex, either forming PDMS or some elastomer, some resist. And we obtain a semi-toroidal joint. So this adds small mass to the moving part and some stiffness also. I will not discuss these points. And okay, now we must actuate the microspeaker, and actuating the microspeaker, we have some alternatives. The first alternative is to use a ring magnet, so to put here. And the purpose of the combination of magnet is to obtain the highest force as possible for a given current. So with one magnet, we obtain 0.05 Newton per ampere. And we studied some alternatives, putting one or two ring magnets, or one cylindrical, or some combinations. So we can see on the slide that for the volume, this has the ring-shaped magnet has some volume, and so the volume of the speaker will be bigger. And so a good trade-off could be using a ring and a cylindrical magnet. Then here you have the complete microspeaker, the microspeaker itself with a ring magnet and the backside ribs, and the complete device on a box with the magnets and the joint. And here, this is a CAD view, and this is a picture of the fabricated microspeaker. So we went to the Mans to test the microspeaker in an anechoic room. It's here, the box is here, the microphone is here, and we tested it with 10 centimeters, so it works. We have a frequency response with this configuration, the ring plus a cylindrical. We have a response from 500 hertz to 20 kilohertz, quite flat at 80 decibels for half a watt of electrical power. So this is nice. And the question is, okay, for half a watt, it gives 80 decibels, but what can it do when the power is less or when the power is higher? So here is the same configuration studied for powers ranging from 9 milliwatts to 500 to half watt, and we can see that it's a nice curve, and that we obtain almost the same quasi-flat response on the bandwidth, so something like 500 hertz to 20 kilohertz, and this seems that the sound power emitted is not linear against the injected power. So here you have the same information, but plotted only at 2 kilohertz from 9 milliwatts to 500 milliwatts. And okay, so we observe that when the power is very low, we have a very quick raise of the acoustic power emitted, and after that, let's say from 100 to 150 milliwatts, the acoustic power emitted is not flat, but almost. So what is the point? So we identified two possible sources for this saturation. So the first source is that when we have magnets, we have air, and so the magnetic field to actuate the microspeaker is not constant along the full range. So this one magnetic field inhomogeneity is one possible source. The second source is the suspension. When you deform a lot the polymer suspension, the joint, it may add some stiffness and then saturate the acoustic power output. So this is we measured the till and small parameters of the microspeaker with a clip-L setup. You have here the laser that measures, I don't see it quite well, but somewhere here is the microspeaker. And so we simulated in dotted lines and measured the force factor on the left. So we obtained, okay, for this configuration, we have quite flat. And we observed that for the configuration I showed before, that the force factor is not constant as we expected. It's dissymmetric, so it's not constant along when the emissive surface moves. The force factor is not constant. Obviously, it's more constant here because it's symmetric. And on the right, you have the suspension stiffness, and here also it's not constant. And for the configuration I showed before, the cylindric plus annular ring, annular magnet, we have a high variation of the suspension stiffness. So this can be an explanation for the limitation of the acoustic power. So okay, we have dissymmetric mechanical structures, magnetic structures. So we have dissymmetric response and saturation of the output power. And another explanation that can be guessed from these results is that when you put a structure like that, the air can move up and down, but putting here a cylindrical magnet below the emissive surface, when the displacement is high, there is a squeezed air film, so this will limit the movement of the surface for high displacements. So this is my last slide. So we have MEMS loudspeaker, silicon MEMS loudspeaker. I didn't show it, but it has because the surface is very stiff and able to move, we have very low harmonic distortion and intermodulation. And it seems that we reached the limits of our device because we can obtain 80 dBs from 500 to 20 kilohertz. And it's obtained at 200 milliwatts, and it doesn't move a lot from 200 to 500 milliwatts. And for the acoustic limits, the limits come from the inhomogeneity of magnetic field and the suspensions, and some things that I didn't say, and we are trying to know what it is. So now we have a quite complete study of a microspeaker. So the question is it going to go to the industry? It's an open question. I thank you for your attention, and that slide is my sponsors.